Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so thank you all for coming. It's an absolute pleasure to introduce Ehsan Ayoub Qazi, who's an assistant professor at LUMS. Before that, he did his PhD from University of Pittsburgh. So Ehsan and I have been kind of friends for more than a decade now. We did our undergraduate together at LUMS, and then we were apartment mates in Pittsburgh as well. And more recently, we have also been collaborating, which is going great. So Ehsan will talk about some of the stuff that's going on in his lab. Okay, so over to you, Ehsan.
Thanks a lot, Fahad. So I'll be talking about a couple of recent projects that my research group has worked on. And before that, I'll give you a quick background about my research group. So I head the Networks and Systems group at LUMS. And we work on three broad areas. One is cloud computing and data centers. The other is wireless networks. And the third one is smart grids. That's quite a lot of areas to actually look into. So I'll describe briefly sort of the key themes within these areas that we're looking into. So in the context of cloud computing data centers, we've been looking into how do we design protocols and frameworks for meeting low latency requirements of large-scale cloud applications. And secondly, we have looked into recently on data center architectures for maximizing efficiency and resilience. So our recent work looks at how do we realize virtual network abstractions which are resilient. Thirdly, we have worked on efficient routing mechanisms, topology design, and management frameworks for data centers. In the context of wireless networks, our work has focused on three broad themes. One is gigabits per second Wi-Fi. So there are lots of MAC layer challenges involved when you go to hundreds of megabits per second, gigabits per second. How do you address them? Secondly, we have also looked into specific design considerations for developing regions. So our recent work has focused on enabling real-time applications using long-distance Wi-Fi. And so this brings in a very interesting cost aspect to the design. And finally, we have worked on supporting real-time applications and bulk transfers on Wi-Fi networks. Our third focus has been on smart grids. And in particular, we have worked in this space because Pakistan, like many developing regions, has been hit by a lot of load shedding. It's not uncommon to have 8 hours of load shedding in Pakistan. So we have worked on three spaces in this particular area. One is peak load reduction. So the infrastructure provisioning in smart grids basically is based on peak load. So if you reduce peak load, you have opportunity for reduction in load shedding. So we have looked into appliance scheduling algorithms in this space for demand shifting. Secondly, we have looked into parsimonious models for demand prediction. So doing a lot of survey and collecting a lot of inputs from people is hard. And so prior work in demand prediction assumes a lot of input from the individual homes. So how many people are there, what kinds of appliances are there. So the focus here is, can we use a very small number of input to be able to predict demand reasonably accurately? And that has implications for lots of applications. And finally, we have looked into models for enabling reliable power through renewables. In this talk, I'll be focusing on two recent projects, one on data center networking and the other on wireless networks, hence the sort of the more general title of my talk today. That was the reason for this. So let's dive into our recent work on cloud computing and data centers. So we have recently worked on a low latency data center networking, and the context, so you can reduce latency on many fronts. So the context of our work has been essentially transport frameworks and buffer management frameworks. So that's the context, and the first two works have been geared towards private data centers or production data centers owned by companies like Google, like web search applications and such like. And then the context of the final work has been both in private data centers and cloud data centers. So if you look at transports that are hard to deploy in public clouds where the end host stack is not under the control of the operator completely. So in those contexts, buffer management frameworks come into play. So I'll focus on PASE, which will appear in SIGCOMM this year. This is joint work with several of my students and colleagues. So Ali Munir, so a subset of this work was done while Ali Munir was an intern at Microsoft Research working with Fahad. So I'll start with that. So if you look at user-facing online services in the last couple of decades, we've seen the emergence of these online services like web social networking and advertising systems. And a key goal in such services has been to minimize user response times. And response time matters because it impacts operator revenue and user experience. So for instance, Amazon found that every 100 millisecond latency costs them 1% in business revenue. Similarly, Yahoo found that an extra 400 millisecond reduced traffic by 9%. And so this begs the question, why is the network important here? And if you look at typical data center applications, they have many distributed components, and it's not uncommon to have those components interact via the internal data center network. So for instance, a Bing search query oftentimes touches more than 100 machines. It's not uncommon for that to do so. Similarly, measurement results have shown that network can impact application performance. So this study, which was conducted over the Bing data center, showed that 10% of research responses observed 1 to 14 milliseconds of network queuing delays. That's orders of magnitude larger than the round-trip propagation delays you have in data centers, which is in the order of 100 microseconds or so. And if you look at data center network resource allocation categories, so there are essentially two broad categories. One is fair sharing. And so the idea is that on a single link, you divide that link equally among flows, given enough demand from the flows. And it's well known that fair sharing leads to suboptimal flow completion times. And therefore, if the goal is to minimize completion times, the traditional fairness metrics are less relevant. So transport protocols like TCP, data center TCP, they focus on fair sharing. The second category is quality of service aware or scheduling approach, as I call it. So the idea is to prioritize some flows, which are typically short over other flows, in order to minimize flow completion time. So on a single service system, for instance, SRPT, which is shortest remaining processing time first, is known to minimize the mean completion time. Similarly, the goal might be to maximize the number of deadlines met. And this is what DQ, which was work done at Microsoft Research, SIGCOMM 2011, I think, that aims at. And along with these challenges, data centers also have their inherent challenges, as you might be aware of them. One is the way the applications are architected. So partition aggregate structure is fairly common, which leads to synchronized loss responses, leading to issues like TCP incast. And you have traffic workloads with diverse requirements. So you have short flows, which are typically latency sensitive. So in the search context, these might be the query traffic and the small control traffic. And then you have long flows, which are typically needed for data updates, maintaining consistency, replication. And these are typically throughput sensitive. And it's well known that TCP-based deployments are unable to meet the requirements of these applications. TCP has this buffer filling nature, which leads to large queues and impacts the latency of short flows. So as a result, in the last few years, we have seen a lot of work on data center transports. And these are excellent pieces of work. One category is of works like DQ, pFabric, and PDQ. And these works achieve near optimal performance, but are not deployment friendly because they require changes in the data plane. So they require changes in the switches. The other category of protocols include data center TCP, deadline aware TCP, low latency DCT, and these are deployment friendly but are suboptimal in terms of performance. So in this work, what we do is that we take a step back and ask this question that rather than right away proposing a new protocol, we ask the question, what design insights can we leverage from existing proposals to come up with a transport which is both deployment friendly, that is, it does not require changes in the data plane, as well as achieve near optimal performance. So that's the target. And towards this end, what we did was that we analyzed existing transports, and we distilled what were the underlying transport strategies that these protocols used. And they turned out to be 3 transport strategies. So the first transport strategy we identified was that of self-adjusting endpoints. Essentially, this transport strategy is essentially where each flow independently adjusts its rate based on network conditions. So data center TCP, D-squared TCP are these protocols, which essentially leverage the self-adjusting endpoint strategy. The second strategy is that of arbitration. So there is a global arbitrator which decides the relative share of the flows. And so protocols like DQ, PDQ, Bharat, which is another work to appear in SIGCOMM this year, follows this transport strategy. Similarly, the third transport strategy is that of in-network prioritization. So protocols like pFabric, you have in the switches, you have priority queues. So each switch essentially independently schedules or drops packets within the switches. So that's pFabric, for instance, does that. Unfortunately, if you look at transports, they only use one of these transport strategies. All the transport strategies only use one of them. And these transport strategies have their strengths. They also have their limitations. So for instance, it's well known that if the protocols which employ self-adjusting endpoint strategy, they are easy to deploy, but they do not support strict priority scheduling. As a result, you have flows which might be low priority, but they continue to send. So essentially, they do not support preemption of flows, which degrades performance. Similarly, if you have arbitration-like approaches like DQ and PDQ, they support strict priority scheduling because they assign explicit rates to flows, but the challenge is high flow switching overhead. So it takes about 1 to 2 round-trip times for flows to change their priorities from low priority to high priority. And if you look at data center flows, it's not uncommon to have a large fraction of data center flows which span only 1 to 2 round-trip times. And so this can be a sizable fraction of the overall response time of short flows. And we showed in our paper why at medium to high loads how this becomes, this flow switching overhead translates into increases in response times. And if you look at in-network prioritization, it helps in reducing the flow switching overhead because you have multiple queues. And so when the top queue isn't full, you can serve the later queues. And but the challenge with it is there are 2 challenges with in-network prioritization. One is that you have limited number of priority queues in switches, which leads to degraded performance, and also the fact that the decisions are switch local. So you might be assigned a particular rate, but your packets might get dropped later on, and so this decisions are switch local. As a result, your performance is suboptimal in certain cases. And we make the case that all these strategies must be used in unison or synergistically because they complement each other. They help addressing the challenges in individual strategies. So I'll give you two examples of how the challenges might be addressed in the ones that I outline. So the first one challenge with in-network prioritization is limited number of queues. And why is that problematic? So suppose you have 2 queues, a high priority queue and a low priority queue in the system, and you have 4 flows. So now you have flows with these priorities 1 through 4. So you have more flows than the number of queues, flow priorities, than the number of queues you have. And if you come up with a static mapping of priorities to queues, it leads to multiplexing. And in any priority scheduling system, you would like the highest priority flow to be receiving the entire share if it is able to saturate the link. But in this particular case, it can lead to multiplexing, which degrades performance. And if you combine this with arbitration approach, so if you have in-network prioritization along with arbitration, you can address this challenge of limited queues in existing switches. And the way you can address this, you can dynamically map flows to queues. So for instance, the highest priority guy can get mapped to the top queue, the rest are mapped to the low priority queue. And as this guy finishes, you dynamically change the mapping of flows to queues. So you are able to address the issue that you get of only in-network prioritization approaches. Similarly, if you look at arbitration alone approaches, there are 2 key challenges with that. One is high flow switching overhead. The other thing is that it's very hard for such approaches to compute precise rates. So for instance, suppose you have 2 flows, one with priority 10 and the other flow with priority 20. Suppose that the arbitrator decided to give 1 gigabits per second to this guy and paused the other flow. And the question is, what if the high priority flow can only send at 0.8 gigabits per second? So if you have non-network bottlenecks, which might be receiver socket buffer or the sender socket buffer, it's very hard for arbitration-based approaches to actually know of that. And so they employ different kinds of things to actually overcome that, which leads to other issues. So the key problem is that when you have non-network bottlenecks, calculating precise rates is hard. And so if you combine arbitration approach with self-adjusting endpoints, what you can do is that since self-adjusting endpoint has this nature of probing the network, so it can grab the remaining 0.2 gigabits per second. So you are able to maintain high network throughput by combining arbitration approach with self-adjusting endpoints. So similarly, we have several examples in our paper on how in-network prioritization and arbitration can be combined to reduce the flow switching overhead that you have with arbitration-only approaches. So PASE essentially uses these insights in its design. And so the key design principle of PASE is that each transport strategy should focus on what it is doing, what it is best at doing. So if you look at the arbitrators, they should focus on interflow prioritization at coarse timescales or at RTT timescales. And endpoints should probe for any extra link capacity which might be in the system because of for instance, non-network bottlenecks. And in-network prioritization should focus on per packet timescales prioritization or sub-RTT prioritization. And so here is the overview of PASE. So we have an arbitration mechanism which is implemented as a separate control plane. This is not part of the data plane. So data plane approaches require changes in the switches. So this is unlike PDQ and DQ. So it's a separate control plane which is implemented, and the output of the arbitration is essentially a reference rate and a priority queue. So flows obtain that, and based on that, so the end hosts essentially use that reference rate, and then they essentially use a more guided rate control. So they use that reference rate as a pivot, and then they can increase and decrease their rates around that reference rate, which is given by the arbitration. And finally, for in-network prioritization, we leverage the existing queues in switches. So let's now talk about PASE arbitrations. So every link essentially has a dedicated arbitrator with PASE. And that arbitrator essentially decides the reference rate and the priority queue on that particular links among all the competing flows. And what the source does is that the source picks the minimum of that, the minimum reference rate of the priority queue. And so whenever you have an arbitration mechanism which is part of the control plane, there are three key challenges that arise. One is of arbitration latency. So every flow has to sort of potentially go to an arbitrator. And if these are really short flows spanning 1 to 2 round trip times, that this latency of going to the arbitrator can be a significant fraction of the overall response time. The second challenge is processing overhead. So if every flow has to go to the arbitrator and requires a measurable processing, that might be a scalability bottleneck. And the third is network overload. What fraction of link capacity is actually being used by these arbitration messages or control overhead? So the way we address these challenges is by leveraging the tree structure of typical data center topologies. And this leads us to follow what we call a bottom-up arbitration strategy. So on the right-hand side, we have an illustration to explain that. So the end-to-end path between a sender and a receiver is essentially divided into two halves. So the left half is essentially taken care of by the sender. So the sender or the leaf nodes, they initiate arbitration. So and on the left half and on the right half, the arbitration is essentially initiated by the receiver. And so the sender obtains arbitration feedback from here, and it obtains arbitration feedback from here, and it picks the minimum rate and the priority queue to use up. Now, a question that comes to mind is why use such an approach? So it turns out that if you look at intra-rack scenario, you don't need to go to the arbitrator at all. So essentially, the sender has a local arbitrator which is responsible for reservations on its link to the Tor switch. The receiver is responsible, has an instance of arbitrator running locally, which is responsible for reservations on this particular link. So for intra-rack communication, you don't need to go to the arbitrator. So you avoid any network latency overhead, arbitration latency overhead. And this is important because intra-rack traffic is a sizable portion of data center traffic, because there is an explicit notion of rack affinity in data centers. And for inter-rack communication, this kind of an approach, bottom-up approach, lends itself to several optimizations, which I'll describe. So I'll focus on the delegation optimization for inter-rack scenarios, but early pruning is also one of the optimizations which helps in reducing the overhead with the control plane arbitration. So in delegation, essentially what happens is that we reduce the arbitration latency significantly by making arbitration decisions as close to the sources as possible. So here is the high-level structure. So with delegation, what we do is that a link with capacity C is essentially divided into n virtual links. And the parent arbitrator essentially what it does is that it delegates the virtual link to the child arbitrator, to load arbitrator. So it allows them to make reservations on its behalf. And the child arbitrator does arbitration for the virtual link, and this virtual link capacity is updated periodically based on the flows arriving in different parts of the data center network. And so that was the delegation optimization, which reduces the arbitration latency significantly and therefore helps short flows in the inter-rack communication scenario. Then we have self-adjusting endpoints. So based on the arbitration decision, which is the reference rate and the priority queue, we have a rate control protocol which uses the feedback from the arbitrators to decide the rate. So essentially, the top queue uses essentially the reference rate, and then you have the middle queue using the data center TCP control laws, and then the bottom queue essentially uses a base rate, which is equivalent to, I think, 1 packet per round trip time or less. Loss recovery becomes complicated because you have low priority queues where packets might be buffered, but they might not get an opportunity for transmission. So we use large round trip time, large retransmission timeout for lower priority queues in order to avoid timeouts. And we also use small probes to reduce the overhead of spurious timeouts in this particular case. So now I'll quickly talk about evaluation. So we carried out evaluation of PASE on a small-scale testbed and NS2 simulations. We considered web search and data mining workloads. We compared our protocol with deployment-friendly protocols, as well as with best-performing protocol in terms of completion times. So here's the structure of the topology comprising of 10G and 1G links, and we had round trip times and buffer sizes which reflect what we have in typical switches. So here is a graph of the application throughput, or the number of deadlines met as a function of the offered network load. So the blue curve is that of data center TCP, and the green curve is that of D-squared TCP, which is deadline-aware TCP protocol, and then we have PASE, which is red. So essentially, as you increase the offered load, increasingly the application throughput degrades for these deployment-friendly transports. And with PASE, its strict priority scheduling approach improves performance by making sure that higher fraction of flows actually meet their deadlines. Here is a graph of the average flow completion time as a function of the offered load for comparison with best performing scheme, which is PASE, which is pFabric. So relative to pFabric, up till 40-50% load, PASE performs comparably, but as load increases, PASE significantly outperforms pFabric. So in conclusion, PASE synthesizes several transport strategies while being deployment friendly, and its performance is comparable to or better than the state-of-the-art protocols that require changes in the data plane or network switches. And one of the interesting aspects of PASE is that it's a modular design which helps in enabling innovation a bit, because the reason for that is that you have in-network prioritization, which is decoupled from arbitration, which is decoupled from self-adjusting endpoints. So if you come up with newer arbitration algorithms, you can actually do almost like a plug and play into the transport framework of PASE, and that would be good. So which helps in evolution. So that was our work on PASE. So if I'll take any questions before moving on to the wireless part. So anything which is unclear or questions? Okay, so I think I should move to the next part. So the next problem, project that I'll describe is that of loss differentiation in high-speed wireless LANs. So this is joint work with several of my students. This work appeared in Infocom 2014. So packet losses in Wi-Fi networks occur for a variety of reasons. So one may be due to attenuation, channel fading, or shedding effects, and we call this noise. And the second cause might be collisions. So two or more nodes transmitting at the same time will lead to collisions and packet losses. And in this particular scenario, you have two nodes which can actually carrier sense each other. So they can sense transmissions, but their back-off counters become 0 at the same time, so they lead to collisions. And the third packet loss can occur due to hidden nodes. So you have uncoordinated nodes which can't carrier sense each other. When they transmit, their transmissions overlap in time, collisions can happen. So loss differentiation is the problem of inferring the cause of packet loss. And why is this important? This is important because different kinds of packet losses mandate different kind of reactions of the MAC layer. So suppose the cause of packet loss is due to noise, or essentially the channel condition was not good. In that case, the action should be to reduce potentially reduce your bitrate, physical layer bitrate. And if the packet loss was due to collision, you need to increase your back-off time. So the back-off protocols which are used by Wi-Fi needs to increase in order to desynchronize the sources and reduce the likelihood of successive collisions. Similarly, if the packet loss was due to hidden nodes, you need to employ coordination mechanisms like RTS, CTS, right? And what happens today is that packet losses are not distinguished. As a result, based on packet loss due to, for instance, noise, you would increase your back-off, which would degrade performance. Due to, for instance, if there was a packet loss due to hidden nodes, you would reduce a bit rate, which will increase the packet transmission time, and in fact, increase the collision probability in the next round. So if you do not distinguish between losses, it leads to performance degradation. And this becomes increasingly important as you move to tens of megabits per second, gigabits per second Wi-Fi. So for instance, if you look at N, it supports up to 600 megabits per second, and 802.11 AC can support more than 1 gigabits per second. And so lack of loss differentiation essentially leads to higher loss of throughput in such high data rate wireless LANs. So the key thing that our work leverages is some of the features which are part of 802.11n and AC like standards. So one of the features to achieve high MAC layer efficiency is frame aggregation. So with frame aggregation, multiple frames are transmitted on every channel access. So in the traditional 802.11 ABG networks, on every channel access, you would only send one packet. In this, multiple frames are transmitted per channel access, which amortizes the overhead. And the second thing is that when you have multiple frames, they leverage the block acknowledgements. So they have a bitmap in this block ACK, which contains information about which frame was received successfully, which frame wasn't received successfully. And so our work essentially leverages these features for loss differentiation. And the key observation that we make in our work is that if you look at noise, collision, and hidden nodes, they result in a distinct structure in losses within aggregate frames. So an AMPDU, or aggregate MAC protocol data unit, is essentially it's essentially a combination of multiple MPDUs. So I'll use the term AMPDU to describe an aggregate frame. And so it results in a distinct structure in losses within AMPDUs and AMPDU retries. So at a high level, essentially, if you look at packet losses due to noise and due to collision hidden nodes, you can tell apart noise from collisions and hidden nodes based on the number of consecutive losses within aggregate frames. And you can tell apart between collisions and hidden nodes based on the retries, the X retries, which I'll describe in a bit. So in this work, we proposed BLMon, the burst loss monitor, a loss differentiation scheme that leverages the distinct structure in losses without requiring any protocol changes or customized hardware support or out-of-band communication. And so as a result, BLMon can be deployed in commodity devices using only driver level changes at the center side. So we conducted a measurement study on a real 802.11n testbed to validate our observation that losses show distinct patterns. We designed and analyzed BLMon. We proposed metrics to quantitatively capture the distinctness and patterns, and then we proposed BLMon, which uses a joint distribution of these metrics in order to infer the cause of loss. And finally, we implemented this in the ATH9K driver and conducted evaluation on a test bed. So I'll quickly go over, firstly, the measurement study that we carried out. So this was an indoor test bed that we had on our campus. And we had a variety of links with a wide range of packet error rates. So this particular link, for instance, the minimum packet error rate that we observed was 0.01%, and the maximum was 28%. Similarly, we have several other links. So we also had very lossy, highly lossy links, like with a minimum PER packet error rate of 41% and a maximum of 99%. So these variations were essentially due to shadowing effects, different objects and due to multipath fading. All nodes used the Ethros ATH9K driver, and the maximum retry limit was set to 4. And when this retry limit is exceeded, or a frame is retransmitted 4 times, then it is counted as an X retry. So this is important because I'm going to talk about X retries in a bit. We used a variety of MCS indices, bit rates, and multiplexing modes. And here are the results for the noise loss analysis of consecutive loss. So if you look at this particular graph, this is the CDF of consecutive losses within an aggregate frame. And this is a link with a minimum of 0.01 and maximum of 28% packet error rate. So the key thing to take away from this graph is that more than 90% of the AMPDUs, they had less than 6 consecutive packet losses. And if you look on the right-hand side, this is a graph. This is a CDF of consecutive losses on the most lossy link that we had, which had a maximum packet error rate of 99%.
How many frames are in one of these aggregates?
Maximum of, by the standard, maximum 64. But in our implementation in the ATH9K, the maximum 32 frames.
And you always sent 32 in this?
No.
Okay.
So we did not change the number of frames actually we sent. It's dynamically adapted by the ATH9K driver. Yeah. And so in this particular case, we had at least 60% of the losses which had 60% of the AMPDUs had less than 15 consecutive losses in this particular case. So the key takeaway is that if you look at consecutive losses, they tend to remain small across a wide range of packet error rates. Then this is the CDF of the X retries. This is the AMPDU retries. And so we explicitly label X retries differently. So for more than 4 retries, we label it as X retry. So this is on link 1. So the key takeaway in this particular case is that almost all of the MPDUs did not experience any retransmissions. So this is in the absence of collisions. This is only due to noise. On this particular side, we have the more lossy link at various MCS values. So in this particular case, only this guy, which is MCS 13, experiences a significant fraction of retries. But 2 key points are that there are 0 or negligible X retries. More than 4 retransmissions are very rare, which is this X retry part of the site. And the reason for that is that if you look at retries, when do retries happen? Retries happen when you have the PLCP header preamble getting corrupted or the block ACK gets corrupted. Now, the PLCP header and preamble are sent at the basic rate, which is much lower than the data rates that you use for the MPDUs. So as a result, they're more robust to channel conditions. So that's the analysis for the noise loss case. Then now we move on to the collision loss analysis. In this particular case, we only had collisions. And And so here is a graph, or here's a CDF of the consecutive losses. So observe that the loss pattern here is much more bursty in the collision case. And then we have, this is the ARET, or the AMPD retries that we have. So less than 60% are retried one or less times. And so majority of AMPDUs are retried only 2 times, and X retries are also negligible. And the reason for why X retries are negligible is because you have backup mechanisms. So every time a collision happens, you increase your backup window, which desynchronizes or reduces the probability of successive collisions. And so the X retries are also rare in collision case. Then this is the hidden node analysis. In this particular case, we have hugely bursty losses. Almost all losses experienced were of 15 size. And on the right-hand side, we have the CDF of the AMPD retries. So observe that more than 80% of the packets experienced X retries. And the reason for that is that because of frame aggregation presents an opportunity, and it also presents a challenge, because now you have large number of frames that you send at the same time. So the amount of overlap could also be significant. So because the nodes are uncoordinated in hidden nodes, this increases the likelihood of successive collisions with aggregation, frame aggregation. So now we design, I'll talk about some of the metrics that we designed to actually capture the degree of distinctness in these patterns. So the first metric that we designed is, we call that the Best Isolation Index, that characterizes the degree of isolation between losses. So this is simply the fraction of the number of 0, 1, or 1, 0 transitions, where 0 is a lost AMPDU or failed MPDU, and 1 is a successful frame received. This is MPDU, and divided by the total number of failed frames. As a result, if you have alternating sequence of losses and successes in your aggregate frame, the BII is 2. This is the maximum value that you get. And if you have bursty losses, then BII tends towards 0. So the more closer to 0 you are, the more the bursty losses are. And if you have all successful frames received, then BII is undefined. So here is a CDF of BII for in case of noise loss at 10%, 40%, and 50%. So when you have a packet error rate of 10% and 20%, a significant fraction, more than 70% of the MPDUs actually had a BII of more than 0.5. However, as the packet error rate due to noise increases, then you start getting more bursty losses. So for instance, the BII for about 50% of the MPDUs was close to 0. And here is a CDF of BII due to collisions and due to hidden nodes separately. So observe that now for about 70% or more AMPDUs, you had BII which is much less than 0.5. Beg your pardon? Sure.
To read this right, is this not monotone?
This is not monotonically increasing?
So if you have more, if you have a high percentage, you're not pushing the line up.
So you're
Why do
talking
they
about
cross? Why do those lines cross?
Oh, why do these lines cross?
Yeah.
Oh, right.
Why are the lines not in the same order as the?
Right. So this is essentially BII calculated on each block acknowledgement. So there is, due to randomness because of shadowing effects and such, like you have these variations in traces. So like I showed, there is a minimum PR, there's a maximum PR. So there's a lot of variation due to noise that you encounter in this particular case.
So I should read this as I can essentially not distinguish between 10 and 40%.
Between 10 and 40% at very high BII values. Yes.
Why?
So essentially, the key takeaway is you need to, if you look at this graph, if you look at this particular point, then you have a majority of AMPDUs having larger than 0.5 BII.
Okay, so if you look at that point, then I do not have the monotonicity I would expect, because the 10% line is in between the 40% line and the 70% line.
Right. So here is the cross, and my understanding is that it's because of the variations that we have in the link characteristics. So this is
at the point 0.5. Why is the 10% line in between? 70% line and
Why is the 10% line in between? Okay.
Should it not be below? Or is the labeling just...
Yeah, it's just labeling.
Right. So I think one thing is that I should have, I think, mentioned the MCS index that we used, which we did not use. And my conjecture is that based on different MCSs, you have different multiplexing modes. And that essentially leads to different kinds of behavior based on, so you can either send two streams, same streams on two antennas, or you can send a single stream on both antennas. So that has different properties, but I need to double check with this. You're right. I think some information is missing here as far as the MCS index is concerned. Yeah. And if you look at the CDF of BII for hidden collisions and collisions, we have BII values for majority of frames which are less than 0.5. And the second metric that we use is simply AMPD retries or ARET. And in that particular metric, so this is the CDF of ARET for noise loss at 10, 40, and 70%, and HCL and CL. And in the hidden collision case, we have large number of X retries that we observed. And we did not observe large number of X retries in both the noise case and the collision case. The third metric that we use is that of history-based packet error rate. So if you look at so AMPDU PR is the per AMPDU packet error rate, which was in one aggregate frame, and PR is the short-term history of the packet array, which is smoothed based on a weighted moving average. So the blue curve is essentially the history PR, history-based PR, and the red spikes are the AMPDU PRs. And so essentially you can observe the sharp increases in the history as well as the instantaneous packet error rates, and we leverage this for actually detecting collisions. So BLMon essentially uses all these three metrics together in order to maximize the detection accuracy while maintaining low false positive rate. So essentially we use a very simple way of combining these strategies. There are several strategies which are possible, which we haven't looked at. So essentially with BLMon, if a BII indicates a highly bursty link and X retries in the last few bursts are high, if we observe X retries in the last few bursts, then we conclude this to be a hidden collision. If BII indicates a bursty link and the AMPDU PR is greater than the history-based PR by some threshold, we conclude this to be a collision loss. Otherwise, and all the remaining ones, if the first two conditions are not true, then we conclude this to be a noise loss. And we only apply burst loss monitor up till a certain PR. So if the packet error rate, if the link is really noisy, then it's very hard to tell apart what was the reason for loss. And so, and in our testbed, this came out to be roughly between 75 to 80%. So beyond 75 to 80% packet error rate, we would not actually use BLMon. Yeah.
So it's the idea that you figure out these thresholds for a given network, and then you apply them, or are the thresholds sort of robust across?
So we tried various set of thresholds. This was an indoor testbed, and these thresholds were specific to the environment that we used. But our understanding is that they for indoor environments they work fairly robustly. That would be our insight. But
even with people moving around, because these are wireless nodes, a lot of them are going to be
right. So we also carried out experiments in mobile settings. So I'll show you the results in a bit. But yes, for different kinds of environment like outdoor settings and such like, you may need to reconfigure the thresholds. But with the environment that we looked into, which was typical indoor with the variety of links, these were fairly. These thresholds gave us fairly. They were fairly robust in different settings.
Because what I'm worried about is when your network is deployed, you're not going to have ground truth on. So you can't dynamically learn what the thresholds are, right? You have to do it in a controlled experiment where you know the cause of the... So then that has to be robust.
Absolutely. I agree with that. And that is why in our evaluation we evaluated BLMon with the threshold, with various thresholds, and we also evaluated in the wild when we had uncoordinated devices. That's a very good point. So we implemented BLMon in the ATH9K driver. And so the PR is already maintained and updated on every block X. Retries and X retries are already reported. And the only computation we add is that of BII, which requires essentially linear scan of the 64-bit block ACK bitmap. So these were some of the scenarios that we evaluated BLMon. So we considered static clients, UDP with collisions, UDP with sources with hidden nodes. We tried with UDP with varying sending rates, with TCP clients. We looked into mobile clients. OK, so quick result on this is UDP with collisions and hidden nodes. So this is only for the y-axis is the throughput. On the x-axis, we have the number of nodes in the network. So this is with BLMon off, and this is with BLMon on. So as you increase the number of nodes, what we observe is that we gain a larger improvement in throughput. So 2.7 times improvement in throughput when you have 6 nodes. So the reason for that is the larger number of nodes you have, the more opportunities you have for collision and telling apart between collision and due to noise. On the right-hand side, we have the throughput as a function of the number of nodes with hidden collisions. So this is without BLMon. This is BLMon on. And what we do here is when we detect a loss due to a hidden node, we do not change our rate, our physical layer data rate. And in this particular bar, what we have is that in addition to not changing the rate, we also enable RTS-CTS. So we gain a larger improvement in throughput. Then we had TCP with the static clients. And here, the improvement was approximately 1.9 times. So TCP's congestion control algorithm kicks in, which reduces the rate if you have large number of successive tries. And we had, so this was in the mobile setting, and this was in the static setting. And and so there's a lot of excellent work which has taken place in this space. So one body of work is requires a customized hardware support. So there's SoftRate, which essentially uses physical layer confidences and to compute the interference-free bit error rate. And then you have Zigzag for hidden collisions. Then there are protocols like Cooley, which requires changes in the protocol or an out-of-band communication. And then you have approaches which use RTS-CTS dynamically to actually differentiate between losses. BLMon does not require any of these things. It simply looks at the block ACK bitmap and tries to infer the cause of loss. And in conclusion, BLMon differentiates losses while incurring low overhead, uses features which are part of emerging standards and existing standards like N and AC, frame aggregation block ACKs. And it only requires driver level changes, and it can improve throughput significantly. So this is all possible because of a fantastic group of students I have in the NSG. And these students have worked exceedingly hard, and they're brilliant. I have 2 PhD students also. So one of my PhD student who was part of the PASE work, which I presented in the fest, he attended the MSR summer school and had a lot of fun. Kamran, so the wireless work that I presented, he worked on that work. And there's a considerable focus on undergraduate research at LUMS. So if you look at these body of works, papers which appeared recently in venues like Infocom and SIGCOM, the red colored names are those of undergraduate students. And they all have received a range of offers from leading universities in the US. So we have received offers, our students have received offers from MIT, Stanford, CMU, Cornell, and such like. And that's all I had. Thank you.